we will discuss this thing, all calculations which we have done throughout these 2 sessions, like turbulence intensity calculation, Reynolds stress calculation, and quadrant analysis, where we do the calculation of contribution of occurrence probabilities. So as you can see, this study belongs to the degraded channel bed of sand gravel mixture, wherein in channel I have placed sand gravel in one test section. If I go back on that photograph, then probably we would be understanding much. See, this was the flume. This you can see here, and in this flume, from this is around 16-meter long flume with sidewall, glass sidewalls were there, and you can see this wooden tailgate. That is a tailgate which was provided in the at the downstream end to control the flow, to make uniform flow initially. I will say initially. Right? So you can see this yellow line which is depicting the test section. So when I say the test section, that means our sediment, which I have been talking, sand and gravel. So the sand and gravel, they were placed in this test section. This test section was around 6 meter long, and I think 0.15 meter deep, around 15 centimeter deep it was, and this width of channel was 0.75 meter, that is 75 centimeter. So this sediment was placed in mixture of sand and gravel were placed in equal proportion, and both were uniform in size. And was uniform in size with median size of 0.27 mm, and gravel was also uniform in size, with median size of 3.1 mm. Right? So both were mixed by weight in equal proportion, and then they are placed on this test section. Now, as you see, when water would be released from here, when we release the water from here, water will come into the channel, and it will transport the sediment. So when this transport of sediment will be collected on the trap, which is placed on the downstream side somewhere, it would be collected there, and from that trap you again refeed the sediment here, so as to maintain the equilibrium. Do you understand this?
Yes, sir.
Yes. To maintain the equilibrium, what sediment we collect here, so we take back those sediment and we again refeed here, so as to maintain the equilibrium. If you consider the equilibrium in river, so at any section, the sediment passing through the section would be equal to whatever sediment is reaching to that section, to maintain the continuity, sediment continuity equation. Right? If that imbalance takes place, imbalance in the sense, suppose let me go back to my this one. Suppose at a particular section in a channel, you have a channel here, this is a river, and you consider a particular section here, one control section. Right? My writing is not too good, please bear with me. Right? So whatever sediment load it is coming from here, that is, if I write this is sediment load, right? And whatever sediment load which is going out, this QT1, and if this is QT2, so this is equal for equilibrium. Right? Now if this condition is disturbed, what will happen? You will tell. What will happen?
Silting and scouring.
Silting and scouring, right? In which case silting would be there?
Sir, greater than to silting and less than to scouring.
Okay, good. Harsh bhai, Harsh Patel. Vaishali?
Hello, sir. जी, sir.
Yes. Do you agree with his
Yes,
answer?
sir.
Yeah. Do you agree with the
जी, sir.
answer? Which in first case you observe silting or,
Uh,
or scouring.
you for
Yes. This condition, can you see the condition? QT1 is greater than QT2 and QT1 is less than QT2.
yes. Second,
What would you observe in the
second
first
one.
case?
QT1 is less than QT2, sir.
What will happen?
Yes.
See, I got answer here. Silting in first case, scouring in second case. Do you agree with this answer? That's what my question is.
Scouring.
See, let us take by this data. Suppose
Yes, sir.
50 ton per minute. That is the sediment coming. This one and this 40 ton per minute. Right? So what will happen? The transported from the section 2 is lesser than the coming, which is coming on the section 15 ton per minute. So naturally, it has to get deposited here on the channel itself. So that is silting, or you can also say aggradation. Hers, is it correct? Nirav?
The first one would be silting.
Yes. So either aggradation or silting we will say, and in second case when QT1 is less than QT2, suppose this is 40 ton is coming from one section and taking out from another section is 50 ton per minute. So what will happen? It will take the sediment from the sediment bed. So what you will observe is scouring. That we can also say the degradation. So sediment will be removed from here and you will have like this profile. The bed will become like this. So this would be initially if it is like this, it would be like this. Some dome is here and this is degradation. So is this clear?
Yes, sir.
Yes, sir.
Yes, sir.
Right?
Yes, sir.
So I mean to explain here the degraded bed, how we define the degraded bed. That's what this exercise was done. So going back to our slide. So when this channel section was there, as I have just discussed, now whatever sediment gets collected here, we are just refeeding it and to maintain the equilibrium. Now, if you do not refeed those sediment, then what will happen? Whatever sediment
Falling occurs.
scouring will
Falling
take
will
place.
occur.
So whatever sediment was collected here, sediment load was collected by trapped here, that was not refeed. So in that case, we got the development of degraded section. And how it was degraded section? See, this is one. Just I'll go in that photograph also. Now this one. So if you see this figure clearly, this is the drawing which we have made. Now this is solid apron and this one 6 meter length test section which I have just shown in the photograph, and this is what schematic diagram of the degraded shape. So initially sediment was filled up to this level. That was the initial bed level you can see here. Right, this is initial bed level. Now as sediment was not refed, means it was not refed on the upstream side, so flowing water will take away the sediment from the bed and it will be creating a degraded bed. So what we are discussing here, that is the turbulence statistics, all turbulence characteristics which got developed in this degraded bed of the sand gravel mixture. So preamble is confirmed. Do you know what we are going to discuss? That's what I have just taken from meanwhile.
Yes, sir.
Right? So the preamble, the submission is that whatever degraded profile is developed, we are going to discuss the turbulence characteristics, turbulence statistics, or coordinate analysis in this degraded bed. So this we will keep in mind. Now I'll go back to my initial this one. Right. So as we know that knowledge of detachment and transport process of sediment is necessary for solving various problems like soil erosion and catchment, reservoir sedimentation. We know that stable channel design, river morphological computations, etc. And in most of the alluvial rivers, sediment transport is usually accompanied by formation of bed forms, and the flow resistance and turbulence statistics of such flow are different from the flow through the stream having plain bed. So now I would like to enunciate here streams having plain bed. One is plain bed, that means there is no development of bed forms, and another streams where you will have number of bed forms developed. So the thing would be different. Now, in this, turbulence is one of the main controlling factors which determine the character and intensity of the river processes. Now, understanding of turbulent flow structure and its relation with the process of sediment transport mechanism is also needed for the prediction of riverbed degradation. So here we want to correlate this riverbed degradation with turbulent flow structures. How the things are happening in the degraded bed with the measurement of velocity using acoustic Doppler velocity meter throughout the degraded bed at 3 sections. Right? Now, different boundary conditions in the case of mobile bed flow makes turbulent flow structure to be different in the flow through erodible beds than the flow fixed bed stream. So now two things, probably in tomorrow or day after tomorrow, you will also see that turbulence statistics in fixed bed stream. When I say the fixed bed stream, what we can say, what exactly we mean by this fixed bed stream? Anybody from audience?
The slope is constant. Slope is constant, sir.
Slope is constant. Okay. Anything else? Deepak?
So the dimension are constant.
Dimension of channel are constant. So we can say the lined canal, even slope is constant, that is also partially correct. But if you have cement concrete lined canal, that is a fixed bed stream. So the turbulent flow condition or turbulent structures would be different in fixed bed stream compared to the mobile bed stream, which we are just discussing, that is the degraded bed. Okay. So turbulence characteristics of flow through a degraded profile of channel bed of sand gravel mixture, that is investigated using an ADV, acoustic Doppler velocity meter. Now you are very well conversant with this term, this instrument. Yesterday Professor Sudhanshu has discussed more about it. Right. So as just I have shown to you, that is the flume. You can see this flume, which is of 16 meter long, 0.75 meter wide, 0.5 meter deep, tilting flume located in the hydraulics engineering laboratory of civil engineering department at IIT Roorkee. And this flume has a test section of 6 meter length. This probably which I have shown in the next slide. 6 meter length, 0.75 meter wide, and 0.3 meter deep. The depth of the test section was 0.313 meter, starting at a distance of 8 meter from the channel entrance. So what is that 8 meter exactly? From here, this distance was 8 meter. This total length is around, how much was the total length? 16 meter. So I have left 8 meter here, so that flow could be fully developed when it reaches to the test section. Because initially, if you see the flume, when water is coming into the flume, lot of turbulence is there. So we have to allow certain length so that the turbulence subside and flow is fully established. So that much length, 8 meter was kept here. Then 6 meter, 8 plus 6, 14, and 2 meter was here, somewhere here. So that makes the total test section, and 0.13 meter was the deep. Right? So these observations were made at various slopes of flume ranging from this 2.417 to 5.8 into 10 raised to -3. Now these are the geometrical dimensions of the sand material. We just have shed median size. We understand median size for just a layman question for anybody. What is median size? D50. How we can define?
If effective size.
Which one?
Effective size.
No, effective size. Anybody else? Median size?
Sir, after the sieve analysis, the
Yeah.
average size of the particle should be less than 50 millimeter.
Percentage of particles, sir, which are smaller, 50% particle, the size of particle which is 15%.
50% is smaller than this size. Percentage finer. If you
Yes.
if you take or if you go for the particle size distribution, or why it is kept or why it is said median size. The reason is when you write the lecture chale if you write 10, 20, 30, 40, 50, 60, 70, 80, 90, right? From 0 to 100. Which is median size here? Statistics. भाई जो मिडिल साइज होती है वही तो मीडियम साइज होती है is it?
Yes, sir.
So if you take the 100% is finer when you plot your particle size between particle size and percentage finer. Everybody would be knowing like this. So from 0 to 100 you go here, and 50% that is median size. So D50 we calculate like this. So this is here what we have got, this one. Right, so median size D50, that is the 50% finer than this size, 0.23 mm, and geometric standard deviation also we define, that is the sediment terminology, while gravel has a median size of 3.1 mm. So this two sizes, you can imagine 3.1 mm is quite large, around 1 inch, more than 1 inch size, and this is 0.23 mm. Both are mixed by weight and 50% weightage, and then that has been placed here, and water is allowed to pass. Then we do not refeed sediment, and then this degraded bed profile was allowed to develop. Right, so up till now, every audience? Yes?
Yes, sir.
Yes, sir, clear.
Yes.
Fine.
Yes, sir, clear.
So now you can see this was the ADV which we have already seen. It was meant by one stand, and so that we can move it. Now it can be lowered down, it can be made lifted up, and this water profile, this degraded profile is there. Water is flowing with certain depth, and this person is setting it and getting the ADV. This cord is connected to computer where we can get the reading. So this was just a pictorial representation. This we also have seen this test section, degraded bed profile. Now there is only one thing to say to you, that this ADV measurements have been taken on 3 locations. So from the beginning of test section, the first station was kept here. Then away from this first station, 0.5 meters, second station was kept, and from here this 1 meter away from this third station was kept, and it was just kept randomly to get the data, the velocity measurement from these zones. Had it been another station here, 0.5 meter, it could have also been done. So you would have 4 stations. But I do not have much time to take the reading, because one reading takes itself 2 to 3 minutes, and this 3 station itself is a lengthy process. So I opted to have only 3 stations, one at section 1, 0.5 away from that section 2, and 1 meter away from the section 2 is section 3. So these are the ADV measurement stations. Now from here, if you see from the channel bed to the water surface, this is the water surface. Now you have to lower its your ADV from this channel bed surface starting from here, and you have to shift this by 1 centimeter each, and you have to go up to this one. the total depth is suppose 16 centimeter or more than that, including this degraded bed, then probably numbers of observations are also very large. Now I can also show you this run data, this one. Now you can see probably, right? So this is one sort of data which was collected. You can see that X is the distance from 0 to 6 meter, the test section 6 meter. Delta Z, that is the depth of the degradation, 9.4 centimeter at 0 section, then 11.4 centimeter, and so on. It is reducing, and finally at this one, 1.4 centimeter. Now you can see the depth measure, that is 16.3, 19.3 onwards, and finally you get in the range of 11. So if you go back here, this one. So from here, this water depth is measured up to this section, which I have shown the data. Similarly, the depth of degradation is also measured throughout from 0 meter to 6 meter. Right? And then you can see this is a sample calculation for particular run on 300 minutes. The observation is taking then 360 minutes. After 1 more hour, what is the change in depth of degradation? Because it is a continuous process. Degradation is a continuous process. As you could have known that in downstream of the reservoir or downstream of a dam, degradation takes place for the number of years. Do you agree with this statement? Yes, audience, please.
Yes, sir.
In case of the, suppose you have constructed a dam and which is storing water up to this HFL. So because of all sediments are trapped here, you have degradation here, because considerably clear water is released from the reservoir. So to maintain the equilibrium, whatever this water particles or water velocity will pick up this sediment, and you will have this degradation on the downstream of the dam. Okay? This is known, is it?
Yes, sir.
Okay?
Yes, sir.
So this degradation process continues for the years. It is a continuous process. You can see up to 10 years, 15 years, this degradation is going on. So accordingly, these observations have been taken in the laboratory flume for for one run. If I start from here, the C15 is one run, 30 minutes, 90 minutes, 180 minutes, this is over now, because there was no change in the degradation, no change here. But if you see this run, CLGS3, 180, 300, 360, 480, up to 480 minutes, there is no considerable change in the depth of the degradation. This 7.7, 7.9, 6.2, 6.7. So almost it ceases. 2.5, 2.5. These values are same. So when we think that degradation is likely to stop, or it is ceasing up, so we can stop taking observation and we can start recording all this velocity data. Right? So this is one sort of data. Even we can see we have gone up to 420 minutes, 7 hours total. Yes.
Sir, there is one question.
Yes,
Sir, if there is a newly built dam,
yes.
then on the upstream side, aggradation happen or degradation will happen on the upstream side for a newly built dam.
Newly built dam, see, degradation will always take place on the downstream of the dam, and on the upstream side you will have aggradation, that we call as reservoir sedimentation or aggradation.
Okay, sir.
So for newly built, even after some years, you will have certain depth of degradation, because it is a slow process. So maybe after 6 months or 1 year. But at the same time, this protection on the downstream side are also done by model studies. In suppose in Gujarat, Gary is there. They do perform model studies to protect this degradation on downstream side.
Okay, sir. Thank you, sir.
All right. So going back to our this section, so we have seen this observation, how the velocity is recorded, and throughout different durations that has been done. So this is schematic representation. Now these are the hydraulic parameters which are collected during the experimentation. You can see the Reynolds number, it is quite high. So it is fully established turbulent flow in which the observations are taken. Bed slope is there, discharge is around 77 liter per second, here around 69 liter per second. And this was which I was talking about, that section 1, section 2 and section 3. So all this section 1, section 2, this one 1, 2, 3. That's what I am writing here. H, what is the H value? 21 centimeter. What is the velocity here? This is again average velocity, Q upon area, taking the average depth at that particular time, and depth of degradation. This is D, depth of degradation. At section 1 is this much, section 2 is this much, section 3 is this much. Likewise, for all 6 experimental run, these data are available, and the Reynolds number is quite high. Right. So taking all these observations, now we have plotted mean velocity for different runs, which I am showing only here for 3 experimental runs. So if you see, this is U average. So whatever U average you have calculated for say one data, 1500 data I have given, it was 4500, but I have given only 1500. So you have taken average of that, say 84 centimeter per second. So that was somewhere here at this location, somewhere here. So that is on one location which we have taken reading. Similarly, you can see the number of points. If you count 1, 2, 3, 4, 5, 6, 7, 8, probably the 16 points are there for this triangle. So section 3, I have taken observations at 16 different points across the depth of the channel. And then I have calculated the mean velocity, which we have done by taking the mean of the data. And that has been plotted here. Now it has been non-dimensionalized by, we are not plotting directly U prime, this U bar, rather than we are dividing it by the mean velocity, which just I have shown here. This one, this mean velocity is there. So this is divided by here. Now this Z by H, that is again the depth. 0 would be considered as original bed level. You can see this 0 is Z by H is 0. That is original bed level. If you go on negative value, that means below the original bed level, the degradation area, and Z by H is positive, that we are going above the bed level. So let me go back to that figure again here. See, or this figure, this one. This would be treated as original bed level, right? And below this bed level, we will have Z by H minus. Above this bed level, we will have Z by H positive. As the what was there? This one. So this was the water depth. You can see the water depth, and this some dark area, that is sediment. You can see here. So the initial Z by H 0 is this level. If you have Z by H minus, you are going below. Z by H positive, you are taking your observation above this bed level. So is this clear now?
Yes, sir.
So you will always see the negative value. That's what I am just again showing you. Negative Z by H would be it would be below the this initial bed level. Below this initial bed level, that will be plotted. So you can see here at bed the velocity is very less. Now whatever velocity distribution which is there, which we usually plot, if you see how the velocity distribution is plotted, it is like if you have y here and u here, so velocity distribution is how it is like this. It's u maximum around at the top, and at bed it is around 0. It is assumed at bed. So but we cannot take the reading at the bed, we generally take just above the bed. Bed सपोज पिटॉट ट्यूब से रीडिंग ले रहे हैं या एडीवी से ले रहे हैं, तो बेड पर तो रीडिंग ले ही नहीं सकते. So you can extrapolate it, but your first reading is somewhere here. So we are starting from here.
Sir, I have one question.
Yes, please.
Sir, while taking the reading with the ADV, so
Yes,
ADV it takes the samples from say 5 mm distance, okay,
yes, yes, yes,
for calculating the velocity.
yes.
So, suppose we want to calculate the velocity at a depth of say 20 centimeter. So, do we have to set up our instrument at by including the 5 mm depth means at 2.5 so that we can take the measurement at 220 centimeter? Is it so?
You mean to say that 20 centimeter from the bed level you are saying?
Yeah, yeah. Suppose, yeah. Say we are
Yes, sir.
we want to take the
Yes, then you have to
measurement
keep it up at 5 centimeter away from that point.
from that point so that
Yes,
it can
yes.
take the
Then you
value.
will get the reading of 5 centimeter below.
Okay.
Yeah.
Yeah, that is fine.
But
Yes.
is
So
it is it
when we keep
suppose
5 centimeter away, we get the reading at the lowermost bed surface, shall I say? So that 20 plus 5, 25 centimeter would be the position of ADV. Yes, absolutely right.
yes. So isn't it suppose we want to take the readings at the bed so we can adjust it so that it we can adjust the height so that it can take the reading at the bed, because you just mentioned that we can't take the reading at bed, so that's
नहीं,
why
टचिंग टू द बेड तो पॉसिबल नहीं है मिनिमम जैसे कि
Means
5.
you have, yes.
Yes, once please.
Actually, if you want to take the reading of bed when you are keeping your ADV just at 5 centimeter from the bed, then it will give the distorted readings. Means continuous fluctuation you will get. Most of the values are negative and they have no sense. So if you see the past literature, then you will find that we will check very close to the bed, but exactly at 5 centimeter it is not means. You
जैसे
are not able to get the
जैसे
exact
आप
reading. So at
बोल
least
रहे हैं
5.1 mm or 2 mm you can keep it up.
दीपक दीपक बोल रहे हैं
Danish, I think.
Dennis, okay. Dennis, see, even we try to take the reading near to bed or at the bed. So as Sudhanshu is saying, till ADV does not get the sampling volume. तो जैसे आप 5 सेंटीमीटर ऊपर रखते हैं, अगर वो बेड से टच हो रहा है तो उसको सैम्पलिंग वॉल्यूम पार्टी वाटर का मूवमेंट मिलता ही नहीं है. तो रीडिंग्स वुड बी देयर, बट दे वुड बी लाइक ऑकवर्ड रीडिंग और इरेगुलर रीडिंग. दैट इज ऑफ नो यूज. So in that case, you have to lift it up, थोड़ा सा ऊपर करेंगे. Then the movement of water, it faces the movement of water and sampling volume. Then probably it gives the correct reading. तो वो आप करके भी देख सकते हैं इवन चैनल में कि how long away from the bed you are getting first good reading. I need to say.
okay. Okay, thank you, sir.
So this was for the different experimental run. I am showing just for the 3 experimental run the mean velocity plot between this ZYH versus U average, and again just we have discussed that 3 sections velocity is there. So depending upon the discharge velocity is changing, this could have been the lesser or higher value. You can see this one. Right? Then this is for remaining 3 more run, mean velocity for experimental run 4, 5, 6. I have just shown you the data of those run, experimental run 4, 5, 6, 1, 2, 6 run. Now this was the stream-wise velocity record for an experimental run at 3 different heights. So I tried to take that from I tried to plot those data which we had got from the ADV for 10 seconds. You can see this 10 seconds, but at 3 different heights. So the idea to plot or to show to you this was just the variation. See, when you have ZYH minus 0.52, that means it is very near to bed. I can go this one. See, this is ZYH minus 6 here, minus 6 here. So ZYH 0.52 is somewhere here, the almost first reading, which is possible or which was possible. So you can see mostly the velocity is negative. Even very few values are there, they are above the 0 line. If you draw the 0 line somewhere here, very few values are there, they are having this positive value, other than all observations having the negative u. So near the bed, we can say the negative or downward movement is there. Then moving little away from the bed, z minus h minus 0.26, you can see this is increasing 0.20 to 80 centimeter per second. This is in centimeter per second. So even few values are there, they are having some negative, other than all are positive values. And if you go up, zyh 0.45. Now let me show you 0.45. Where it is? Somewhere here. Zyh 0.45, somewhere here. 0, have a 0.3, somewhere here. Right? So you can see no value is negative. Velocity is always positive. There is, if you draw the velocity vector, I mean to depict this thing. Why? If you want to plot the velocity vector, then at this height you will have the forward direction vector. But at this point, if you draw the velocity vector, you will have minus value, which is moving like this away from the water or opposite to the water direction. So this simply without doing analysis, one can conclude that near the bed velocity is negative, and as you move up, the velocity is changing from negative to positive value. You can see the near to water surface. This value is near to water surface. All values are more than 100 centimeter per second, around even more than some are 152. Right? So is this clear, Saman?
Yes, sir. Clear, sir.
Yes. So this was the velocity record. Now the same thing which just I had spoken, that was converted into the vector plot. So now this line shows the degraded channel bed section in all 4 cases. This was plotted vector on the vector side. Now you can see, as I have just said, that this all are the negative. Here you can see the negative. This is denoting the magnitude of the velocity. So you can see the maximum velocity at the top. It has 0 velocity or negative velocity. Here you can see in this lot of negative velocity up to this. zy0 is the initial bed level. This is initial bed level. तो नीचे आप देख सकते हैं कि सभी में नेगेटिव है और बहुत कम है. But to be very true, on the third section, this is on third section, section 1, section 2, and section 3. Just I am saying that section 1, section 2, section 3. And to make you remind, this was first section, this is second section, and this was third section, very away from the degraded bed channel. Right? So in the third section, you can see all vectors, they have a sufficient value of velocity, and that is increasing near to the from near to the bed to the top surface. So you can see another run number 5 here. Again, the reverse flow, we can say the reverse flow, or you can say the vortex structure, because this flow is moving in opposite direction. Water is moving like this, but velocity vector is showing this opposite direction. Right? So this is plotted in I think vector plot. One of my colleague has done. I have not done this. Probably he is going to demonstrate you tomorrow. Tomorrow he is going to take one lecture where he would be depicting you how these vectors can be plotted. And not in this, but he has done his study in scour around piers. So he would be a very right person to say about this. Right now, then turbulence intensity, which you have calculated yesterday, again for the same 3 sections, section 1, 2, and 3, and for the throughout depth, that zyh0. Now you can see what important thing we have to note here, that the variation is like this. If I take this dark block dots here, now where the maximum value is around this zyh0. So it is increasing from bed surface to the initial bed surface, that is zyh0, and from that value zyh0, it is again reducing and going to the minimum value. So this is normalized, or we can say dimensionless value by dividing it by the shear velocity, which I have spoken or we have discussed yesterday. So that is there. and this is for 3 run, and similarly you can see for 3 more runs. So you can again see in this also in run number 5, 4 and 5 and 6. So this is going like this. And you can also see one more important thing. See, if you have section 1, 2 and 3. So section 1 has a lot of variation in turbulence intensity, but if you take section 3, almost same value you are getting. See, almost same. There is no much variation. And that means turbulence has settled when water has reached here. If I go back on this section drawing again, see this one. So maximum turbulence is here at section 1 in terms of turbulence intensity. At some turbulence is there at section 2, and as water reaches up to this section 3, more or less whole turbulence has settled. So that's what we are getting a lesser amount, means variation is not there, whatever range is there, but there is no much variation as you go across the depth. It is all right, Neerav?
Yes, sir.
Fine. Anjay, Lakshman? Because see, it is fourth length session, and you could be lazy also at any point, so I have to make you awake. आपको थोड़ा जगा के रखना पड़ेगा ना.
Yes, sir. Yes, sir.
So that's what in between we can have a little talk. Otherwise, it would be one-way delivery. I am speaking from here, and you people are means listening although, but not present mentally, only present physically. Right. So this is variation of turbulence intensity, and similarly, we can also get the variation of Reynolds shear stress as you have done your exercise. That was for one data. We have done for across the whole depth. And in this also you can see in the section 1, this is the variation. See, like this, and it is minus u. Now this is plotted only u prime w prime we have plotted. We did not take v prime w prime and u prime v prime, because those although your software will give you all 3 values, but you can also see out of the 3 only u prime w prime is the most dominant. So I have plotted that only. And you can also see in this initial section that zy at 0, you have the maximum value. So it is having maximum in the sense in negative, because it is negative. So this will go to the maximum value here, changing in this case also, and even, and all other this one section, run 4, 5 and 6. So as I have shown you total 6 run data. So whatever calculations have been done, they have been done for all 6 experimental run. And again, in this case, this zy at 0, these stresses and turbulence intensity are maximum. That means this vortex structure, or at the initial bed level, as sediment is picking up from that bed level, these values are responsible for that sediment picking up, ejection and sweep. That we will also see.
Sir?
Yes.
Hello.
Yes. Yes, please.
So if the sections are constant for each run?
The observations at where the section at where the observations are taken. You mean to say that? Yes.
Yes, sir. Actually, आपका जो data है वो सर वो 6 run का है, तो all of the 6 run the section are constant? Section is same?
Yes. The location of section which I have shown initially, that was same for all 6 runs. This one which we can see here, this first section, section 2, section 3. But in all 6 sections, the discharge is varied. Accordingly, the depth of degradation is also changing. You can see in this 5th run, the degradation is like this 9.54 centimeter, 12.84, 12.4 at 3 sections. Similarly in this section. So varying the discharge and creating different degradation condition, and once degradation developed, the observations have been taken. but at the same section, same locations. Is it all right, Dennis? Yes, probably I think he has lost connectivity. Can you hear me, Dennis?
Yes, I can hear you, sir.
Yes. So question was this from Deepak or Dennis?
The question was from someone else. I didn't
Someone
ask
else.
the question.
Okay, fine. Right. So this was about the Reynolds stress. Now, quadrant analysis, as we have discussed in the morning, although it will take a lot of time to do the quadrant analysis, because at one location you have so much data, and that data has to be segregated into 4 quadrants and then determining the occurrence probability, and you have to go for whole points. Suppose you consider this section 1. So this 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, whatever, 15 points. So all 15 points for a one run and all 3 sections. That much time you have to segregate your data to go for the quadrant analysis. Hopefully, I understand that you can understand the intensity of work incorporated or involved in that. Right. So in morning, as we know, that is outward interaction, ejection, and inward interaction and sweep. So that quadrant analysis was done to identify the busting trends and occurrence probability of these events. Now in this, you can see this occurrence probabilities for event type across the flow depth for run number 6. This I have shown only one run here. So for run number 6, from ZYH minus 0.6 to ZYH around 0.4. So you can say the whole depth is covered, and these occurrence probability, these are calculated. You can see the sweeping and ejection, this 2 cross and this square. These have the maximum value. You can see wherein outward interaction and inward interaction, they have minimum value from 0 to around 15, and this is for h equals to 0, which you did in morning. Your morning में हमने exercise की है where we have kept h equals to 0. We did not change the value of h, and segregating all those and calculating the probability, and for all points from bottom to top, rather not from top to bottom to top, determining this SIH. So for h equals to 0, and then for h equals to 1. So what I did it for a particular location, I have to run the program, then I have to calculate this value of all 4 events, then I can get plot on this. Similarly, on another point, I have to run the program, and so on. You will be running your program and getting all these 4 value, and then you can plot it on Excel, keeping this probability on x-axis and it on the y-axis. Right? So now, what thing we have to observe here? While going from h equals to 0 to h equals to 1 and h equals to 2, you can see the probability SIH is reducing. See here, for sweeping, you will get around this, how much? I think it is around, how much it would be? 35. It would be 35% if you have h equals to 2 compared to here h equals to 0, it would be around 40% or 45. This is 45 because this is 50. Right here it is near out 40. So when we have been discussing in morning, what is the importance of h? So weaker events, if you one thing is that you consider h equals to 0 so that you incorporate all the events. But if you have numbers of data large, suppose 6,000 data or 10,000 data, so in that case, if we want to remove the like some absurd data or weaker event, then in that case we can go up to h equals to 2 to produce the probability of stronger event only, and that can be plotted on this Excel graph, which can be shown here, h equals to 0, 1, and 2. Right? So that is occurrence probability. Now Whatever we have shown here, the plot can also be generated in this form, taking all those data, all data of all outward interaction, ejection, sweep, and inward interaction. We can also develop this one. The occurrence probability of plotted against whole size. So what I have taken, the whole size from here 0 to 15 on this x-axis, right? And on the y-axis, we are having the occurrence probability. So you see here, outward interaction, it is here, this one, sorry, 0 is here. So when h equals to 0, it has certain like 0.18 value or 0.2 value, 20%. And as you increase this h value, this is reducing like this, right? Similarly here, in this 0 to 15 in this way, this is maximum at 0 value, ejection is maximum at 0 value around 30%, and then it is reducing to somewhat near 5%. Similarly for inward interaction, it is increasing from 0 to 15, sorry, decreasing from 0 to 15. 0 it has maximum value around 10% or something, maybe 15%, and then it is going, and this is for all three sections together. The notations are same, section 1, section 2, and section 3, that I have not given. So this plus triangle as well as this square. So this I can go here. Probably sections notations, they are there in other graph. Right? So now what you can actually match this thing if you see this figure. So more or less this the figure where central zone is whole, which is almost matching here. You can see if you compress this thing, because I have made this on some graph, but if you join, if you remove this gap, make a plus sign here, probably you are getting a tremendous H shape. Whole size, the central size is whole size, that you can get. Right? So this is at 1 ZYH minus 0.52. Now you can also get above the water level. That was, see, ZYH minus 52, that is near to the bed, very near to the bed, because I have done calculation. Now above the bed or just near to the top of the top surface. So in that case also the same thing is plotted. H whole size is there, 0 to 15, 0 to 15 here, and then this 10 minute pachi. So you can also see the same scenario here from 0 to 15 H value. This probability is reducing in all four cases. So hope in morning whatever we have been discussing, that what is the importance of H, probably I hope that little bit of you can make it clear concept of that. Okay. So this is all what it was done in one study where we have gathered the data for ADV at various locations, 3 locations, and then all have been plotted in the form of turbulence intensity, Reynolds stresses, this occurrence probability, and occurrence probability against whole size H, where it was varied from 0 to 50. So to conclude it, I'll read out the conclusion, and then we will have question answer session if any. The experiments were conducted to measure the instantaneous velocity, turbulence intensity, Reynolds stress in channel bed profile that was degraded due to the detachment of bad material consisting of sand gravel mixture. Now an ADV was used to measure the velocity and turbulence data at 3 locations. Just we have seen that at 0.5 meter downstream of section 1, at the start of section, and 1.5 meter downstream of section 1. The maximum value of turbulence intensity and Reynolds stresses was observed to occur at level of the channel bed surface before the start of detachment. Just we have discussed that ZYH equals to 0. That is the start of the or level where the test section is placed. That value, maximum value of these two phenomena was observed. Magnitude of turbulence intensity and Reynolds stresses are observed to reduce as we move towards the downstream along the degraded bed profile. We have also seen that we have maximum value at section 1 and section 2, but if you move to section 3, the magnitude is reducing. Then quadrant analysis have been performed to demonstrate the importance of ejection and sweep phases in sediment detachment and transport. And the ejection and sweep event are noticed to be more dominant over inward interaction and outward interaction. We can also see from that. You can see the ejection and sweep, how much value they are having. They are varying from like 40% to somewhere here 10. Here also it is 40%, so 40, 40, 10, and this is 10, 10 around. So outward interaction and inward interaction, they do not have much impact as the sediment detachment takes place or erosion takes place. That's what it was proved in this study too. Right? So the ejection and sweep events are noticed to be more dominant over OI and II, and highest occurrence probabilities were found for sweep and ejection event, and variation of occurrence probability with hole size also studies. So as the post-plunge session, we would not like to take much here, and you are now conversant with these terms. So quickly I have finished it. Now we can discuss for any question and query if you have. Yes, any question or any doubt?
If there is any question, then you can ask dear participants.
Sir, can you explain more about hole size?
Yes.
The last slide that you have shown the graphs.
Please repeat the question.
Can you explain about that hole size in the last slide before conclusion? What was the x-axis in that 0 to 15?
I think last slide there was some question from us.
Last slide.
Before conclusion, there was probability plots.
Figures. These figures.
Sir, in this, I didn't understand what is the x-axis.
In this figure, you do not understand what is you want to tell. Is it?
The x-axis 0 to 15, what does it mean?
That is, see, in morning class when we have taken I have just shown you the ADA program where we are trying to vary the H whole size from 0 to 15, thereby changing the or eliminating the weaker events in your data. So this was done. See, initial plot when I have seen this or I have shown this. This is for one H value, H equals to 2. These were the occurrence probability of all 4 events. But if you run your program for variation in H from 0 to 15 and you calculate the occurrence probability of all 4 events.
So in Y you are having occurrence probability, and in x-axis you are having hole size. That is the answer for this question. Ma'am is asking what is x and y coordinates.
Yes, sir. So
sir, can you explain about that hole size? What does it? What it
hole
means?
size.
Yeah, hole size is that, see, this much portion. When we are taking our stress function, as in morning we discussed that stress function. So that stress function is plotting these values like here in this pattern. And the central portion which has remained, that is the whole size. And the
will it change with respect to the experiment?
We wanted to replicate rather.
Will it change the hole size will change depending upon the experiment, or it is a fixed one?
Definitely, it would be the function of experimental data. It could be in different shape, but definitely you will have some region in when you plot all four events together. Then you will have some region where these events are not happening.
Okay,
Is it
sir.
clear?
Yes, sir.
All right. Yes.
Sir, I have one question.
Yes, please.
Yes. I want to ask.
Yes.
Sir, you said that we can assume the value of a whole size from 0 to 15.
Yeah.
So is there any way that we can calculate this value, or just we have to assume some values and then make some trial and errors? So means what is the criteria to select a suitable value of this H?
See, in fact, as far as literature is concerned, literature says that the maximum value of H, which you can take 15, starting from 0. Usually, when you take H equals to 0, you means you are involving whole data which you have collected through your ADB observations at different sections or different locations. So H equals to 0 will exactly show you the occurrence probability of all the four events. But again, if you want to eliminate some absurd reading, you can increase. See, I have seen only initially, if you see, I have gone only H equals to 2. I have not shown more than this. This H equals to 0, H equals to 1, just to check. Really, when you are increasing the H value, you are removing some weaker events, and your probability is also changing, occurrence probability. So I have shown up to H equals to 0, 1, and 2 only to get this value. And then I wanted to also have an idea to get whole from 0 to 15. So that's what I have taken these plots. But in literature, it is written that generally 1 up to 2, you can show those values. There's no need to go up to the 15, because if you go up to the 15, you can see the probability becomes 2 less. Here it is around 0.1, less than 0.1 here in ejection, less than 0.1 here, less than 0.1 here. So means you are not even representing the whole data, I should say.
So a good practice be to use the H values from 0 to 2. I think this is the good practice.
Yeah.
Thank you, sir.
Okay, fine.
So is there any other question?
Sir. No, sir.
No, sir.
Okay. So I think there are no questions now. So we can close the session, because we have next session at 3:30. So sir, I think we will give 20 minutes break.
20 minutes break would be fine.
Okay. So 20 minutes break you will have now, and then directly we will move to the third session after 20 minutes. So 20 minutes, 20, 30, 40. Okay. So we will start the next session approx 3:40 p.m.
369164.
3:40 p.m. Okay, we will meet again and continue with the third session by Dr. Manoj Langhi sir. Okay, on the title Use of Computational Fluid Dynamics in Estimation of Turbulence Characteristics. So this is very now you have enough idea of the turbulence.
Yes.
And 1 minute. So now you are having the enough idea of the what is turbulence, what are the turbulence characteristics, what are the different relations, different models for and different conditions like ejection, sweep. So now you can able to get the more information. You can able to grasp what are the application part of these terms. So we will from today's onwards from the third session you will find all the application part. ठीक है, use of computational fluid dynamics in estimation of turbulence, the near bed sediment motion, and there are some changes I think in the tomorrow's session. Tomorrow you will have some change in the lecture. I will share the details afterwards. Okay. I will not take much time. So because we have to meet
it is
again at
expected that
3:40.
you all join by 20 minutes because we have experts
Yes,
from
yes.
IIT and
Yes,
all
we
are
have.
requested.
Yes, yes. So we will start directly at 3:40 p.m. Okay. Thank you all.
Thank you, sir.
Thank you, sir. Thank you.
Yes, welcome.